My name is Luke Monington, and in this video, I'm going to be going through this article that I wrote for Proven Strategies for Dominating NLP Tasks. This article goes in detail about when exactly to use an LLM and when to use a fine-tuned model, and it goes into some background into data consideration and also safety. A lot of the factual information from this article actually came from a research paper, and so I'll link the research paper and the article that I wrote here in the description below. Also, I invite you to follow my Twitter, it's in the description, where I share various different insights and AI breakthroughs as they come. For this video, I'll be reading through the article that I wrote and providing my commentary as we go. So let's get into it. As an introduction, the advancement of large language models has had a transformative impact on the natural language processing field. Not only have these models exhibited capabilities in addressing various NLP tasks and real-world tasks, they're also leading the way towards artificial general intelligence. The strength of LLMs lies in their extensive ability to understand and generate natural language. But using them in an optimal way involves understanding their strengths and weaknesses, as well as the nature of the data and the tasks at hand. It's crucial to recognize when to use LLMs, how to choose an appropriate model, and how to consider key factors such as model size, computational requirements, and the availability of domain-specific pre-trained data. Moreover, it's beneficial to dive into different types of tasks, understanding how LLMs apply to knowledge-intensive tasks, traditional language understanding tasks, and generation tasks. In order to grasp the capabilities of LLMs, it's essential to compare them with fine-tuned models. LLMs are essentially massive language models pre-trained on large datasets without task-specific tuning. Conversely, fine-tuned models are often smaller language models that have been pre-trained and subsequently tuned on a smaller, task-specific dataset to improve their performance on a particular task. The goal here is to provide a background on LLMs and explain the proven strategies in order to utilize them most effectively. So the idea here is that a big difference between an LLM and a fine-tuned model is that the fine-tuned model is going to be a lot smaller. And so that's going to lead to a lot of advantages, but also disadvantages. A smaller model is going to be able to make inferences much more quickly, but a disadvantage of it is that it's going to generalize more poorly. So it really has a lot to do with factors such as the business application in use, the data available, the computational power, the inferencing speed, and a bunch of other factors. And we're going to be getting into all of that in this article here. So to start out, what are the different types of LLMs? The landscape of large language models is rich and diverse, boasting different types of attention mechanisms, model architectures, and use cases. The attention mechanism employed by these models broadly classifies them into three categories: non-causal, half-causal, and causal attention models. Starting with the core components of these models, we have the encoder transformer. The encoder transformer processes an input sequence to produce a detailed contextual understanding of that sequence. It relies on self-attention and feed-forward layers to understand the dependencies among the different elements within the sequence. It's used in scenarios like sentence classification or named entity recognition, where the meaning of the entire input sequence is used for decision-making. So the idea of an encoder is that it takes an input and then converts it into some type of contextual understanding. This can be really beneficial in certain cases, such as when you need to make a decision based upon some text. Another important note with this is that the encoder-only transformer generates the entire output all at once. In contrast, a decoder-only transformer is more causal, so it generates a token at a time. To go back to the article, contrarily, the decoder transformer generates output sequences based on the provided input. It uses self-attention layers along with encoder-decoder attention, allowing it to refer back to the input sequence. The decoder's hallmark is its autoregressive nature, allowing it to generate output sequences step by step, where each element is dependent on the preceding ones. It's often employed in tasks like text generation or machine translation. The encoder-decoder transformer, however, combines the strengths of both encoders and decoders. The encoder forms the representation of the input sequence, which is then used by the decoder to produce the output sequence. This dual setup allows the model to grasp the input sequence's full context and generate an output that reflects this understanding. Such a design finds use in tasks like machine translation. So an important note here is that there is some overlap in the performance of some of the models. So a decoder-only transformer can actually be used for machine translation, such as by asking GPT-4 to translate text. But also, an encoder-decoder transformer can be very effective with a situation like that as well, where the encoder produces the contextual understanding of the sequence, and then the decoder translates it into the language of choice. In recent years, causal attention models, also known as decoder-only models, have gained popularity, notably with the advent of models like GPT-3. These models have overshadowed non-causal encoder-only and half-causal encoder-decoder models. Decoder-only models like GPT-3 and GPT-4 from OpenAI have garnered considerable attention due to their impressive performance and OpenAI's unwavering dedication to its technical direction. And really, an important idea here is that OpenAI seems to be light years ahead of the competition. We've had all these tournaments for these LLMs, and both the proprietary and the open source models still haven't been able to catch up to GPT-4. And as much as I believe in the strength and power of the open source community, especially as it relates to being able to adopt ideas extremely quickly, I think that OpenAI is going to have a huge advantage because they just have so much more data. And because everybody's using the ChatGPT app and OpenAI has the control over that data, it looks like they're in a really good position to be able to leverage this to make a new model that's going to be way more powerful. Going back to the article, in the open source sphere, Meta has made significant contributions by open sourcing all of its LLMs. However, a recent trend toward closed sourcing models, especially following GPT-3's introduction, is worth noting. This shift towards closed source models such as Palm, Lambda, and GPT-4 has made it more challenging for academic researchers to experiment with LLM training, hence promoting the use of API-based research. This is a really interesting point as well, because in the past, researchers were able to work with LLMs on site. But now, as a result of the closed sourcing of the models, a lot of the research that's being done with these models is done through sending API calls. And some examples of API calls that might be made might be using GPT-4 to rate the outputs of certain models, which can be used in a tournament style setup in order to assign ELO ratings to all the different models. It can also be used in a context of AI explainability. So, for example, using GPT-4 to explain the individual outputs of a model like GPT-2, which I talked about in a previous video, and other applications as well. Another interesting point to go on this is that in the past, a lot of these LLMs were created by researchers in research institutions. But what we're seeing now is that these LLMs are getting so expensive to train and they require so many resources. So now in the present, these models are primarily created by large companies and they're not created by the research institutions. Despite the importance of decoder-only models, encoder-decoder models remain promising and continue to be actively explored, with Google significantly contributing to open source encoder-decoder architectures. However, the flexibility and adaptability of decoder-only models potentially calls into question Google's commitment to this direction. So really the point here is that these decoder-only models are really taking the lead. They're very flexible and adaptable, and although companies like Google are pushing these encoder-decoder type models, really the trend that we're seeing is that the best performing models are the decoder-only models. To summarize, non-causal attention models like BERT and Roberta are encoder-only models, and they predict masked words and sentences using their surrounding context. Causal attention models like GPT-3, OPT, Palm, and Bloom are decoder-only models, and they generate the next word in a sequence based on the previous words, aligning them more with natural human speech causality. This characteristic makes them effective for text generation, question answering tasks, and showcasing impressive few-shot and zero-shot performance. Now that we've finished going to the background of the three major types of transformers, let's go more into the importance of the data. The significance of data in the lifecycle of large language models cannot be overstated. It's instrumental during pre-training, training, and inferencing. The choice of data impacts the effectiveness of the models and their generalizability for downstream tasks. This holds especially true when faced with out-of-distribution data like adversarial examples and domain shifts, where LLMs excel compared to fine-tuned models. When there's a scarcity of annotated data, LLMs emerge as a favorable choice over fine-tuned models. However, both can be suitable when there's an abundance of annotated data, contingent on the specifics of the task at hand. Ideally, models pre-trained on data similar to the downstream task tend to be more effective. So the idea here is that if you're going to use an LLM or fine-tune an LLM, the best performance is going to come by finding a model that's trained on data that's as similar as possible to the data that you want to use it on. So for example, if the model is going to be used in the context of science, then it would be good to find an LLM that's pre-trained on an abundance of scientific data. If the model is going to be used in the context of fantasy, then it would be really good to find a LLM that's fine-tuned on a lot of fantasy novels. Pre-training data is of vital importance in developing LLMs as it dictates the model's performance. The data is typically a diverse collection of text sources like books, articles, and websites curated to provide an all-encompassing representation of human knowledge. It equips the model with a nuanced understanding of word knowledge, grammar, syntax, semantics, context recognition, and response generation capabilities. Pre-training data's diversity, quantity, and quality can dictate the selection of LLMs for different tasks. And to give you an idea of how much data is actually used in some of these LLMs, we're seeing datasets that are larger than 1.2 trillion tokens. That ends up taking up more than 6 terabytes of space on a hard drive. And if the trend continues, these datasets will only continue to get larger. Also, models like Palm and Bloom, which excel in multilingual tasks and machine translation, leverage a substantial amount of multilingual pre-training data. Palm's question answering performance is improved by including a substantial volume of social media conversations in book corpus. GPT 3.5 enhances its code execution and code completion capabilities through the integration of code data in its pre-training dataset. Thus, for downstream tasks, models pre-trained on similar data fields tend to perform better. During fine-tuning, the availability of annotated data can dictate the selection of the model for downstream tasks. In scenarios with zero annotated data, LLMs operate in a zero-shot setting and avoid the issue of catastrophic forgetting as their parameters remain unaltered. With few-shot annotated data, few-shot examples are incorporated directly into the LLM's input prompt, a technique known as in-context learning, which aids in the model's generalization to the task. So the idea here is that if there's no annotated data at all, then obviously a fine-tuned model is going to be out of the question since we have no data to fine-tune it on. Also, if we only have a very small amount of data, then the same concept will apply, where we don't want to fine-tune the model because if we do, then the model could potentially become super overfit to the dataset, or even the model could exhibit traits such as catastrophic forgetting, where it completely forgets a lot of the data that it was pre-trained on. If there's abundant annotated data, however, both fine-tuned models and LLMs are viable options. The choice between a fine-tuned model and an LLM would thus depend on factors like desired performance, computational resources, and deployment constraints. So the idea here is that if there's an abundance of data, then a fine-tuned model could perform just as well. And it may even be better because a fine-tuned model could be much smaller, which means that the inferencing time would be much quicker. But there could also be some drawbacks using a fine-tuned model because it's not going to perform that well on out-of-distribution data. In terms of the real-world performance, the disparities between the data distribution in the training phase and the real-world application phase can pose challenges. These include domain shifts or out-of-distribution variations. Fine-tuned models, owing to their specificity to certain data distributions, often struggle with these variations. However, LLMs tend to perform better due to their lack of explicit fitting process. Enhancements like reinforcement learning from human feedback have improved LLMs' generalization capabilities. Therefore, in most downstream tasks, LLMs exhibit superior generalization compared to fine-tuned models. So the idea here is that in the real world, LLMs are going to encounter a ton of different situations that they weren't explicitly trained on. If there's a high likelihood that there's going to be a lot of out-of-distribution data in the real-world use case, then likely the LLMs are going to outperform the fine-tuned models. Now we're going to compare LLMs with fine-tuning in regards to their applications. In the field of NLP, there are traditional NLU tasks such as text classification, named entity recognition, entailment prediction, and others. These tasks often serve as integral steps into the broader AI systems. LLMs are typically trained on vast and diverse datasets without further fine-tuning, which makes them versatile and capable of handling many tasks. However, fine-tuned models usually outperform LLMs in traditional NLU tasks. This can be especially true where there's an ample amount of annotated data available and the test data does not have many out-of-distribution examples. So just to be clear here, this is one case where fine-tuned LLMs truly do shine. Now let's break down the different natural language understanding tasks. First is text classification. In the context of AI, text classification refers to the process of categorizing text into predefined categories or classes. For instance, classifying emails into spam or not spam. In tasks like text classification, fine-tuned models generally outperform LLMs. Next is sentiment analysis. This is a subfield of natural language processing that deals with determining the sentiment expressed in a piece of text. It's often used to identify whether a piece of text, like a product review or a social media post, is expressing a positive, negative, or neutral sentiment. Sentiment analysis tasks like the IMDb and the SST datasets have seen both LLMs and fine-tuned models performing equally well. Next is toxicity detection. Toxicity detection is the task of identifying harmful, offensive, or inappropriate content in text. It's a type of text classification problem where the goal is to determine whether a piece of given text is toxic or non-toxic. This task is particularly important in the context of moderating online discussions to maintain a respectful and safe community environment. Models built for toxicity detection need to understand nuances in context and language, as what might be toxic in one context might be acceptable in another. Fine-tuned models significantly outperform LLMs in this context. So this is an interesting point as well, because I would imagine that a toxicity detector would receive a ton of different inputs that it needs to make predictions on. And so it's really interesting that fine-tuned models significantly outperform in this context. And so the reasoning for this is that there's so many nuances in toxicity detection that an LLM is unable to perform well. And so a fine-tuned model is going to perform way better as long as you have a good data set. Next is the RTE and SNLI. This is a task in NLP where the goal is to determine the logical relationship between two sentences or text snippets. This relationship can be entailment, if the truth of the first sentence guarantees the truth of the second, contradiction, if the truth of the first sentence guarantees that the second is false, or neutral, if the truth of the first sentence doesn't provide enough information to determine the truth of the second. RTE, which is recognizing textual entailment, and SNLI, the Stanford Natural Language Inference, are two popular datasets used for training and evaluating models on this task. Fine-tuned models generally surpass LLMs for these tasks. And so this is interesting as well, because if you're able to predict entailment, then it's possible to create a higher quality dataset, which can then be used to create a better fine-tuned model or a pre-trained model. Next is question answering. And question answering is an area of AI where the system is designed to provide direct responses to questions posed in natural language. This is more complex than a simple text search. The AI model needs to understand the context of the question and provide a precise and relevant answer. For question answering tasks on datasets like the Squad V2 and the QUAC, fine-tuned models typically perform better. And so this is really interesting as well, because in the context of answering questions, which is really critical for some chatbot applications, a fine-tuned model is actually going to outperform an LLM. So if the primary application of the LLM is to be able to do question answering, then maybe a fine-tuned model would perform better. Next is information retrieval. Information retrieval refers to the process of finding and retrieving relevant information from a larger dataset, which is usually unstructured, like a collection of text documents. Information retrieval tasks have not seen widespread use of LLMs. This is primarily because information retrieval tasks cannot be easily transformed into a few-shot or zero-shot form, which is a requirement for LLMs. Currently, fine-tuned models seem to fare better in such tasks. Next is named entity recognition. This is a task in natural language processing where the goal is to identify and categorize specific entities mentioned in text. These entities can be people, organizations, locations, time expressions, quantities, monetary values, percentages, and more. Here, fine-tuned models also appear to perform better. Finally is dependency parsing. This is a task in NLP where the goal is to extract the grammatical structure of a sentence by identifying the relationships between different words. In a dependency parse, words are nodes and grammatical relationships are edges, forming a tree-like structure. This can be useful in many natural language processing tasks, as it provides a more structured representation of the input text that can help a model understand the nuances of the language. Here, fine-tuned models also perform better. In summary, fine-tuned models are often a better choice for traditional natural language understanding tasks, considering performance on benchmark datasets and computational costs. However, the choice between LLMs and fine-tuned models often depends on the specific requirements and constraints of a given task. Both the art of instruction design for LLMs and the potential for improving fine-tuned models hold promise for future advances in NLP tasks. Now let's discuss knowledge-intensive tasks. Knowledge-intensive NLP tasks are a category of tasks in AI that rely heavily on the possession and application of general or domain-specific knowledge. These tasks necessitate more than mere pattern recognition or syntax comprehension. They require a deep understanding of specific entities, events, and real-world common sense. Large language models have an edge in these tasks due to their vast stores of real-world knowledge. However, they may falter if the knowledge requirements of the task don't align with the information they've learned, or if the task demands only contextual knowledge. In such cases, fine-tuned models perform just as well. And so the idea here is that previously, when we were talking about the question answering for the natural language understanding task, that type of question answering task is a task where you give it some context, and then you give it a question, and then you ask it to give a response. But here, now we're talking about answering questions where there is no context, and the model needs to be able to have an internal understanding of the task in order to be able to answer the questions. One application where LLMs excel is closed book question answering, where the model is asked to provide factual answers without any external information. This type of task necessitates the memorization of real-world knowledge. LLMs have proven to be superior in datasets like natural questions, web questions, and trivia QA. Similarly, other tasks that challenge the model's knowledge of various subjects often see LLMs performing above average human level. However, not all tasks align with the knowledge stored in LLMs. Tasks that require the model to extract knowledge directly from the provided context, like machine reading comprehension, can be performed effectively by smaller, fine-tuned models. There are also instances where the real-world knowledge within LLMs is either irrelevant or counterfactual to the task at hand. For example, the MNIST ASCII task in the Big Bench, or tasks that redefine a common symbol and ask the model to interpret it based on this new definition. And so you might be wondering, what is the MNIST ASCII task? And this is actually a task where we map the words in ASCII art form into the actual word. And so it has nothing to do with the actual understanding of the text, but everything to do with actually mapping the art into an actual word. For a task like this, the LLM's pre-trained data is completely useless in order to make the prediction, and so a fine-tuned model would actually outperform. In cases where external knowledge is allowed, models can utilize retrieval augmentation. This involves adding an extra information retrieval step before a prediction, where relevant texts are fetched from a large corpus to aid in the model's prediction. This method transforms a closed book task into an open book one. In such cases, fine-tuned models often perform well due to their smaller sizes, as the necessary knowledge can be obtained through retrieval. So the main idea here is that if it's an open book test, then a fine-tuned model is going to perform well. But if it's a closed book test, then the LLMs are going to outperform. Next, let's look at the text generation task. In the field of NLP, tasks of text generation can be grouped broadly into two categories. The first set includes tasks where the aim is to transform a given text into a new sequence of symbols. This involves tasks such as paragraph summarization and machine translation. The second category, often referred to as open-ended generation, include tasks where the goal is to create new text or symbols from scratch based upon the given input or guidelines. This could be writing emails, creating news articles, or even generating code. Large language models like GPT-3 and GPT-4 are particularly powerful in these generation tasks due to their sophisticated language understanding and creative capabilities. In the case of summarization tasks, while automated metrics like ROGUE might not indicate a clear superiority of LLMs over fine-tuned models, human evaluations show a preference toward the output generated by LLMs. This could be due to better coherence, relevance, and faithfulness of the summaries produced by the LLMs. So this is actually a really interesting piece of information because although the fine-tuned models and the LLMs were performing at the same level on these benchmarks, the human raters actually preferred the LLMs. And so that calls into question whether the way that we're evaluating these models programmatically is actually reflective of real-world performance. Regarding machine translation, LLMs can perform effectively, particularly when translating text from low-resource languages into English. Even though their performance might be slightly lower than some commercial tools when evaluated using metrics like BLEU, they're especially adept at tasks where only a small amount of training data is available, like Romanian English translation. This is likely due to the extensive presence of English language data during the pre-training. LLMs have also shown proficiency in open-ended generation tasks. For instance, they can create news articles that are hard to distinguish from human-written pieces. In addition, they've shown capability in generating code. However, despite their performance, the generated code needs rigorous testing for possible errors, illustrating one of the challenges in applying LLMs in code synthesis. And on this point, I think that in the future, LLMs will be able to create code that is completely bug-free. But at the present moment, LLMs need to be monitored carefully when they're generating code because they can generate buggy code, or the code just doesn't perform its intended purpose. Also, it's important to note that there are cases where fine-tuned models still outperform LLMs. For example, in scenarios involving rich resource machine translation tasks, as well as in extremely low resource translation tasks, fine-tuned models tend to perform better. This highlights the importance of selecting the right tool for each task based on the specific requirements and constraints. This is a really important idea as well, because the idea is that if there's a ton of data, or if there's a very small amount of data, a fine-tuned model might actually perform just as well or even better than an LLM. Next, let's talk about regression. LLMs have found it challenging to excel in regression tasks, which involve predicting a continuous value rather than a discrete label. An instance of this might be evident in ChatGPT's performance on the GLUE STSB dataset, a regression task evaluating sentence similarity where it underperforms compared to a fine-tuned Roberta model. The primary reason for this issue lies in the discrepancy between the core language modeling objective, which centers around predicting the next word or generating text, and the regression task's objective. This situation gets further complicated when dealing with multimodal data, a domain where LLMs have limited exploration. Although GPT-4 has attempted to fuse multimodal data, it is yet to be thoroughly evaluated for its capabilities. One interesting point here is that GPT-4 is getting better at predicting regression tasks, but in general, a fine-tuned model is going to perform better. Now, here are some notes on data augmentation and quality assessment. LLM's adeptness at generating human-like text positions them as useful tools for data augmentation, a technique that expands training data and enhances model robustness. Furthermore, they can act as quality assessors for natural language generation tasks like summarization and translation. For instance, GPT-4, when used as an evaluator, has shown significant alignment with human evaluations. One thing to note here is that although GPT-4 has shown alignment with human evaluations, it does seem to show some biases. So for example, if two inputs are given to it and GPT-4 needs to give a rating for both input 1 and input 2, GPT-4 will typically rate input 1 more favorably than input 2. Also, LLMs offer the advantage of interpretability. For example, the chain of thought reasoning ability of LLMs not only improves their performance, but also provides insight into the model's decision-making process, offering an explanation at the instance level. This interpretability is an added advantage that comes with performance enhancement, shedding light on how these models reach their predictions. So, although we don't understand the workings of the individual neurons, we're still able to get some explainability by using techniques such as chain of thought. Next, how does size impact performance? The size or scale of large language models in terms of parameters and computational power employed during training greatly contributes to the model's potential capabilities. There's an observed correlation between the model's size and its performance across diverse tasks, with some indicators revealing a power law relationship. For instance, in language modeling, the cross-entropy loss decreases linearly with an exponential increase in model scale, a trend referred to as the scaling law. Two major types of reasoning tasks benefit from model scaling: arithmetic reasoning and common sense reasoning. Arithmetic reasoning performance, such as performing two-digit addition, becomes apparent in LLMs once the model size surpasses a particular threshold. Common sense reasoning, involving multiple steps of inference data based on facts, also tends to improve with model size. LLMs often outperform fine-tuned models on many related datasets. As models scale up, certain emergent capabilities begin to manifest. These capabilities aren't typically present in smaller models, but begin to show as the model grows larger. These abilities go beyond the power law rule and emerge unpredictably and surprisingly. Examples of emergent abilities include handling word manipulation tasks like word sorting and reversing, logical deduction, and sequence tasks, and advanced coding or concept understanding tasks. So the idea here is that the smaller models don't have the ability, but then as they grow larger, at some unpredictable point, they suddenly gain the ability to do something. And so this is what's known as an emergent capability. And so they don't follow the power law rule because in the power law rule, the performance improves over time. But with the emergent capabilities, the performance improves dramatically at some unpredictable points. And so while the previously mentioned benefits come with larger LLMs, the performance does not always increase with scale. On some tasks, an increase in model size can result in decreased performance. Also, another observed behavior of scaling LLMs is the U-shaped phenomenon, where performance initially improves with scale, then it declines at a certain point, and then it starts to improve again. Additionally, there are methods to change inverse scaling tasks to U-shaped or flat tasks, for example, by providing a one-shot demonstration or by implementing chain of thought. And so the idea here is that even though the performance is decreasing as the model size increases, there are still ways to mitigate it, and overall, the inverse scaling tasks do end up turning U-shape as the model size gets large enough. As an example of inverse scaling, a task requiring LLMs to redefine common symbols might yield poorer responses as the model scales. Similarly, tasks demanding specific contextual understanding may not benefit from larger models. Finally, gaining a deeper understanding of these emerging abilities and the inverse and U-shaped scaling phenomena is vital for advancing research in the field of LLMs. Though several hypotheses have been proposed to explain these behaviors, there is no definitive explanation. One hypothesis suggests that for emergent abilities, LLMs may need to reach a sufficient size to handle all steps in a task. Another explanation could be that models overly rely on prior knowledge rather than input prompts, or that misleading few-shot examples or easier subtasks within a complex task can lead to these unexpected behaviors. And regarding this point, in my opinion, I think that we're not going to get that much of an explanation until we have a better understanding of the inner workings of the LLMs. So when we get better techniques at explaining the activations of the individual neurons, I think that's when we would have better explanations for why the models are performing as they are. Now let's compare LLMs and fine-tuned models in the real world. In real-world environments, AI models are often subjected to messy, unstructured input data from users who may not know the best way to interact with the model. This input may contain errors, slang, and mixed languages, contrasting with the clean, structured data used for pre-training or fine-tuning these models. Also, tasks in the real world do not always align with academic definitions and are typically more diverse. User queries can be multifaceted, combining multiple tasks into a single request or harboring implicit intentions that the model must decipher. Despite these hurdles, LLMs are generally better equipped to handle real-world scenarios than fine-tuned models. The diverse datasets on which they are trained and their ability to generate open domain responses position them well for dealing with a broad range of inputs and tasks. In contrast, fine-tuned models are optimized for specific tasks and may find it harder to adapt to new or unexpected user requests. And so I think one major thing to keep in mind when deciding whether to use a fine-tuned model or a LLM is how broadly do we want the model to be able to perform? Are there going to be a ton of varied inputs, or is it going to be pretty well defined? If it's generally going to be pretty well defined, then a fine-tuned model would perform better. Some strategies have been devised to enhance LLM's capabilities further, like instruction tuning and human alignment tuning. These techniques refine the model's ability to comprehend and follow user instructions, generating responses that are helpful, honest, and harmless while maintaining coherence. An important note, however, is the difficulty in evaluating model effectiveness in the real world. Given the lack of defined tasks or metrics, currently the primary method of evaluation relies on human feedback. But this process is complex and expensive, making extensive systematic comparisons between fine-tuned models and LLMs challenging. Nevertheless, the widespread use and success of models like ChatGPT suggests that LLMs may hold an edge in these contexts. And so the point is that although we have all these academic benchmarks, those benchmarks may not accurately reflect how the model will perform in the real world. But the success of models like GPT-4 indicate that maybe they do perform pretty well. Now let's compare the models as they relate to efficiency. Efficiency covers aspects such as cost of training, the time taken for making predictions, and how efficiently the model can be tuned. Smaller, locally fine-tuned models could be more appropriate for situations with strict latency requirements or cost sensitivity. Parameter-efficient tuning, which involves adjusting only a small portion of the model parameters, is a promising approach for efficient model deployment. One notable aspect of LLMs is that unlike fine-tuned models, they cannot learn shortcuts for task-specific datasets in a zero-shot fashion. Despite this, they can still display some issues related to shortcut learning. The safety risks associated with LLMs, such as biased or potentially harmful outputs, require utmost attention. And so the idea here is that we can use parameter-efficient fine-tuning to reduce the cost dramatically for fine-tuning a model. And thus, a case could be made that a fine-tuned model might be more effective in a business context. The safety risks associated with LLMs, such as biased or potentially harmful outputs, require utmost attention. Techniques involving human feedback have shown potential in mitigating these issues. When it comes to deploying AI models in real-world scenarios, it's important to factor in not only the performance, but also their cost and latency. Training LLMs is resource-intensive. Larger models require more computational power and energy, which escalates costs. The inference time, or how long it takes the model to generate predictions, also increases with model size and complexity. There are methods available to help balance efficiency with effectiveness. For instance, parameter-efficient tuning techniques like low-rank adaptation, Q-LoRa, prefix tuning, and p-tuning can all be used to adjust only a small set of parameters in the model, reducing computational cost and storage requirements without compromising performance. Despite these methods, the costs and latency associated with large LLMs may still prove prohibitive, particularly for smaller organizations or individual users. In such cases, smaller fine-tuned models could provide a more feasible solution. So what it comes down to here is how many resources the company has. If the company has a ton of resources, a large language model would perform better. But if there's a lack of resources, maybe a fine-tuned model would better fit the requirements. Lastly, it's important to note that larger LLMs often require significant hardware resources and may not be suitable for applications that demand fast response times. In these scenarios, efficiency and scalability are crucial. So this comes down to how quickly do we want the responses. If we need the responses to be extremely fast, then a smaller model can much more easily deliver that. But if the results don't need to be fast, then a larger model would provide higher quality results. Now let's compare the models as they relate to trustworthiness and robustness. The trustworthiness of a large language model is crucial, especially considering their increased application in sensitive domains like healthcare, finance, and law. The term robustness refers to an LLM's ability to maintain accuracy in varying conditions, and it's often positively correlated with the model's overall accuracy. However, zero-shot models, which are capable of performing tasks without any task-specific training data, may see their robustness decline after being tuned on additional data for specific tasks. This is often due to overfitting. When a model is excessively complex, it may fit limited training examples too closely, resulting in reduced generalizability. When models are fine-tuned, they can become miscalibrated due to over-parameterization. Essentially, fine-tuned models may not be the best choice when robustness and calibration are paramount. Human alignment, such as aligning AI behaviors with human values and expectations, can potentially improve model robustness. So the idea here is that if we're training a very large LLM, then we want to make sure that we have a decently sized data set so that our model doesn't overfit to the data. Bias and fairness issues are also notable when discussing LLM trustworthiness. LLMs can unintentionally reflect societal biases, leading to potential disparities in treatment or impact. This can result in significant performance differences across demographic categories such as dialect, religion, gender, and race. However, aligning models with human instructions can help to mitigate these issues, with certain models like InstructGPT showing smaller performance disparities than other LLMs. Spurious correlations or shortcut learning is another problem in NLP tasks. Models may rely on superficial correlations between input and labels in the fine-tuning data for prediction. For instance, in reading comprehension tasks, models might focus on matching words between the question and the passage instead of truly understanding the text. On the bright side, LLMs which aren't directly trained on fine-tuned datasets are less prone to learning about shortcut features, potentially improving generalization. Nevertheless, LLMs can still exhibit some shortcut learning during in-context learning. Therefore, while LLMs can significantly mitigate the shortcut learning problem, care should be taken when deploying them in real-world applications. Finally, let's talk about safety. As large language models increase in sophistication and become more human-like in their capabilities, they pose potential safety challenges that have been gaining attention. These abilities, spanning reasoning, knowledge retention, and even coding, may mean that LLMs significantly influence people's opinions and actions. As large language models increase in sophistication and become more human-like in their capabilities, they pose potential safety challenges that have been gaining attention. These abilities, spanning reasoning, knowledge retention, and even coding, mean that LLMs can significantly influence people's opinions and actions, warranting safety considerations. One such concern is the phenomenon known as hallucinations, where LLMs generate content that is nonsensical or untruthful. As users increasingly trust and rely on these models, there is a risk that they will take the generated content as accurate even when it's not. This could lead to misguided decisions or actions, especially in critical fields like healthcare, finance, or public policy, where reliable information is crucial. To counter this, reinforcement learning from human feedback is commonly used, integrating the LLMs themselves into the feedback loop to improve the output accuracy and relevance. Another challenge is the potential for LLMs to generate harmful content. Given the high coherence and believability of LLM-generated texts, there is a risk of producing hate speech, promoting discrimination, inciting violence, spreading false narratives, or even enabling social engineering attacks. These models might also be exploited for illicit purposes. Thus, it is vital to implement safeguards to detect and correct such outputs, as well as to use these LLMs responsibly. Human feedback is again a vital component in addressing this issue, helping to identify and eliminate harmful outputs. Privacy concerns also pose significant risks, especially with regards to user data. For instance, there have been cases where confidential data, such as source code or internal meeting minutes, were inadvertently leaked. Also, OpenAI, the developer of ChatGPT, faced legal repercussions for illicitly gathering personal user data, leading to the Italian government banning the use of ChatGPT due to privacy concerns. Such instances underscore the necessity of stringent data protection measures when deploying LLMs. That's all for this article. I hope you enjoyed and feel free to subscribe for more content like this.